So, welcome everyone. This is our experiential learning of on the topic green synthesis of nanomaterials for supercapacitor applications. Uh, our team is I, Himamshuji, Chetan Yadav, and Dhanush Kote. So, come to introduction. So, supercapacitors. So, supercapacitors, they are also known as ultra capacitors or electrochemical capacitors. So, they are advanced energy storage devices. So, they bridge the gap between traditional capacitors and batteries. They also offer unique capabilities in terms of rapid energy storage and release, making them suitable for applications that require high power bursts and quick charging cycles. Unlike conventional batteries, which store energy through chemical reactions, supercapacitors, they store energy electrostatically on the surface of electrodes, so leading to several distinct features. So here you can see the one diagram of supercapacitor. So nanoparticles. So nanoparticles are wide class of materials that include particular substances which have one dimension, so less than 100 nanometers at least, and they can use for many applications like in batteries or medicines for and many other fields. So they have potential advantages including increased strength, durability, improved electrical conductivity, and enhanced catalytic activity. So green synthesis. So green synthesis of nanomaterials is a revolutionary approach that combines the principles of nanotechnology with eco-friendly and sustainable practices. So this green synthesis method, focuses on creating nanoparticles and other nanoscale materials using natural or renewable and non-toxic resources, minimizing the use of hazardous chemicals and or toxic chemicals and energy-intensive processes. So the objective here is to reduce the environmental impact associated with the traditional synthesis methods while producing functional nanomaterials with diverse applications. You can see one example of green synthesis of nanomaterial here. So steps involved in green synthesis of nanomaterials for supercapacitor applications. The first one is selection of precursor. So choosing one eco-friendly and sustainable precursor material, so that which can be derived from natural resources such as plant extracts, agricultural waste, or microorganism. The next one is preparation of extract. So using the plant extract, preparing them by extracting bioactive compounds using appropriate solvents or methods to obtain the necessary reducing and stabilizing agent. The next one is reduction and nucleation. So combining the precursor materials with the bioactive compounds from extracts. Then synthesis reactions uh, under good suitable temperature, pH, and reaction time. Then the nanomaterials will form. The next step is characterization. So for characterization, they may use X-ray or TEM, that is transmission electron microscopy, like this. And purification and separation is the next step. So centrifugation, filtration, or other method can be used. Then it should be dried for some particular amount of time. Then further processing or application testing, this suitability evaluation, optimization and scaling up, documentation. Like these are the next steps. And finally, the prepared nanometer will be coated to the electrodes of supercapacitors. So one example is manganese oxide nanoparticles. So the precursor which is used is the leaf extract of the plant called Viola betonicifolia. So the steps involved here are cleaning, as I mentioned in the earlier slide, cleaning, deionizing, blending. Then, so in the experiment, 25 grams of this plant extract is taken and deionized with the water. So then, under suitable reaction will be carried out. Then, as you can see in the flow diagram, then filtration, collection. These are the normal steps. So coming to results. So then it's applied to a super capacitor electrodes. So Dr. Blade approach is used to paste the sludge on the aluminum sheet and dry it outside. Paradic pseudocapacitance created by redox reaction of manganese oxide and activated carbon. So it resulted in increased surface area. And after testing, got to know that the performance of the supercapacitors, it shows good performance. So other one is zinc oxide nanoparticles. So the zinc oxide nanoparticles, the hip plant called Hippis suvalenus, is the scientific name, is collected from Perambalur district of Tamil Nadu. So here initially they're sliced into pieces, then deionization using water, then leaf extracted were in a reflux condenser for half an hour, extracted there. Then they cooled for half an hour, and the solution was filtered using some Wattman filter paper, and gathered filter was stored in the fridge for later use. So then, in a conical flask, the extract and 0.01 molar zinc nitrate solution was added in some particular ratio, like some the ratio is 1:4, and the combination was then agitated for some 4 hours, and resulting mass was dried in a hot air oven. This is the next step, and one yellow paste will be obtained, and it's calcinated around 400 degrees Celsius. The zinc nanoparticles will be obtained. Then further characterization is there. So coming to a result, so several after characterization and testing, the several absorption bands were seen in FTIR spectroscopy, that is Fourier transform infrared spectra. So the bands may be associated with the ammonia carbonyl group or CH bond. Then studies like SEM and EDX were conducted. So EDX spectrum especially. So it confirms that the composition of the nanoparticles and the shape is Wurtzite hexagonal form. It is in the Wurtzite hexagonal form. So size may be 10 to 200 nanometer. And these nanoparticles aggregate due to their high surface energy from being synthesized in aqueous media, and perhaps due to densification, which causes a small spacing between particles. Also, the pattern of rings with spars indicating that nanoparticles have a bigger grain size and a more uniform shape, and they are in polycrystalline in nature. This can be known. And the test is they also demonstrated that the particles are extremely crystalline in nature. So you can see the images obtained after testing. Over to Chairman.
Coming to silver nanoparticles, this synthesis of silver nanoparticles using copper chloride. Here, the solution of silver nitrate AgNO3 was made for this purpose in 25 ml of ethylene glycol. It is slowly added to a solution of 0.05 gram of copper to chloride, which serves as a reducing agent, and 5 to 6 ml of Eg after an hour of vigorous stirring. The solution tints changed to a pale green. The initial mixture of silver nitrate and Eg was then gradually supplemented with this solution drop by drop. The solution color changed to a bluish green blue. Next slide. After the previous process, 5 ml of Eg was added separately to a weighted amount of PVP as a capping agent while being vigorously magnetically stirred. Then it is slowly added to a solution of 0.05 gram of copper chloride, 4 to 6 ml of green source neem, which serves as reducing agent, and 5 ml of Eg after 25 minutes of vigorous stirring. The initial mixture of silver nitrate and Eg was then gradually supplemented with this solution drop by drop. Excited studies of this synthesized silver nanoparticles by copper chloride, neem, henna as reducing agents. Then, due to their high, coming to CO3 C1, due to their high specific capacitance and surface to volume ratio, transition metal oxides, notably cobalt oxide nanoparticle employed as electrode materials. The first step was to dry and the first step was to wash and dry the leaves. Then distilled water was added to the chopped leaves in a glass beaker, and the mixture was cooked for 2 hours. Then the solution was kept to attain room temperature, was filtered and stored. The precursor for the nanoparticle synthesis was CONO3 twice 6H2O. Next slide. Then cobalt salt solution and plant leaf extract were combined, and the mixture was heated at 80 to 85 degrees Celsius for 180 minutes. When CO3O4 and nanoparticles were formed, a color change from light brown to dark brown was evident. The resulting solution was centrifuged and the residue CO3O4 nanoparticles was baked at 65 degrees Celsius. Next thing is characterization. For these various experimental studies like SEM, TM, FTIR, and XRD are conducted using the instruments. Here it has been disclosed a simple, beneficial, and economical salt gel synthetic method for uniformly growing CO3O4 nanoparticles over cheap and environmental friendly one-dimensional cellulose nanofiber surface which is hydrophilic. Next slide. Coming to other nanoparticles, titanium dioxide. Here, numerous forms of nanoparticles can arise when organic acids, proteins, vitamins, and secondary metabolites like flavonoids, alkaloid compounds, terpenoids, and polysaccharides interact. Complexes of carbon nanotubes and titanium dioxide particles must be added to polymeric matrix in order to maximize the device surface area, electrochemical response, and electrical response due to the interaction of EDLC and pseudocapacitor effect. Next slide. Then copper nanoparticles. Here, Hymedia and F-oxysporum leaves that had been collected were cleaned with tap water to get rid of any dust. The dried leaves were ground into a powder in a blender and the powder was kept in a room temperature in the dark. Then the created extract was first vacuum filtered using cellulose, nitrate membrane and Wattman filter paper. The filter was either used right away or put into storage for later use at 4 to 5 degrees Celsius. Next slide. Coming to the advantages, high surface area. Here high surface area means the nanomaterials possess an inherently high surface area due to the nanoscale dimensions. The increased surface area for a greater number of electrochemical reactions to take place at the electrode-electrolyte interface, resulting in high energy and power density in supercapacitors. Enhanced, enhanced charge storage. Here, the nanomaterial exhibit improved charge storage capabilities due to their unique electronic and structural properties. Their small size and high surface area facilitate quicker ion diffusion and adsorption, enabling rapid charging and discharging cycles. Improved capacitance. The presence of nanomaterials with tailored nanostructures enhance the electrochemical capacitance of supercapacitor electrodes. This leads to energy storage capacity compared to traditional materials. Then better conductivity. Many nanomaterials possesses excellent electrical conductivity which promotes efficient electron transfer within the electron material. This facilitates faster charge or discharge rates and reduce the overall internal resistance of the capacitor, enhancing its performance. Then turnability. Here the nanomaterials can be synthesized and engineered to have specific properties such as size, shape, composition, and surface functionalization. This turnability allows researchers to tailor the material characteristics to suit the requirements of different supercapacitor designs and applications. Flexibility and versatility. Here, the nanomaterials can be integrated into various electrode configurations, including flexible and variable devices. Small size and flexible enable the development of lightweight and compact supercapacitors suitable for diverse applications. The other advantages are long cycle life, environmental benefits, integration with other technologies, miniaturization, economic feasibility. Next slide. Next slide.
Mhm.
Mention next slide.
Next slide ಹೋಗಿದೆ.
Coming to disadvantages, these are the disadvantages like cost, synthesis complexity, scale up challenges, agglomeration and stability, toxicity and health concerns, limited supply and resources, performance variation, degradation and stability, lack of standardization, and regularity hurdles. Next slide.
Hmm.
Manju, can.
Next slide ಹೋಗಿದೆ.
In conclusion, the green synthesis of nanomaterials for supercapacitors presents a promising and sustainable approach towards developing high performance energy storage devices. By utilizing natural resources such as plant extracts and microorganisms as reducing agents and stabilizers, the green synthesis method reduces the reliance on hazardous chemicals and energy intensive process associated with conventional synthesis techniques. The use of green synthesis in nanomaterials for supercapacitors has many advantages. They, the green synthesized nanomaterials exhibit excellent biocompatibility, making them suitable for biomedical applications. These nanomaterials improve the specific capacitance, charge discharge rates, and cycling stability for supercapacitor devices. Next slide. These are the references we use for. Thank you.
Thank you.